Hey Data Junkies, welcome back to Statistics with your host, Shawn Janzen. I'm excited to be here with you while we're starting a new module topic on correlations. Correlations are very important. They're always around us and involved with so many different parts of our lives with statistics, even if we don't happen to realize it. And this first lecture video is going to be talking about foundations, interpretations and assumptions, and causality. So let's go ahead and get started. We've got lots to cover. In future videos, by the way, we are going to be also talking about things like how to calculate the correlation by hand, doing these things in R, building correlation matrices, looking at non-parametric versions, the works. So let's get started here. Now, when we're talking about correlations, we're in a family of statistics called bivariate association. We've talked about bivariate association even if we haven't used those words specifically all the time. A lot of the effect sizes you've been doing, like phi and Kramer's V, Cohen's D, Cohen's H, these are all bivariate associations. Two variables to say how related are two variables to each other by some particular measuring capacity. And we're in this bivariate association, we're saying how well can one help predict the other based on their scores. The stronger the association, the better and stronger your predictions are going to be. Now in this case, our bivariate associations seek to answer three questions. First, does this association exist? Second, how strong is the association? So by being a non-zero, it exists, and then being some distance from zero, we infer that it is having some measure of strength. The larger the difference from zero, the stronger the association. And then based on those, we can also talk about a pattern or direction. The pattern or direction is really something that's characteristic for the R and correlations that other particular bivariate associations might not necessarily have. So when we're talking about the correlations here, we're talking about two ways that variables are linearly related. Let me repeat that. The way in which two variables are linearly related. Now, variables can be non-linearly related. They can have non-orders and things like that. The chi-squares had that particular regard for them. So in this case, we're talking about bivariate associations across linear variables. Now, I have up for you a scatter plot here to show the relationship between age and someone's appreciation for rock and roll, with a little Homer up at the top. Rock on, Homer. So what we have here is what I call sort of the buckshot effect. We have data points all over the place, seemingly random, all mishmash all over, and I have a white dotted line cutting through. And this white dotted line is what we call a line of best fit. It tries to find the best way, the best place it can cut through the data where it's going to have an equal amount on both sides of it and minimize the distances of those data points to that line. Little hint here, it's actually a regression line as well that we call the line of best fit, in this case a linear regression line, but we're going to hold that conversation until we get to the next module on regressions themselves. In this case, the line of best fit is just to give us a visual approximator on how these data points are fitting with our correlation. So here, because it's cutting across and they're still all over the place, very far from that line, we're going to infer that there's no relationship between one's age and how much they appreciate rock and roll. If I change this up, we have a different graphic measuring the same things, age and appreciation for rock and roll. However, now the data points are forming a sort of trend. We can see that they start on the bottom left and move towards the upper right. And as it does that move, they move sort of in a cloud together, and that line of best fit has moved to track it. It's bisecting the data the best it can to fit these data points, and that line is moving in an upright direction. This is what we call a positive relationship, because as age increases, so does one's appreciation for rock and roll. Check this against the third graphic here, where it's moving in a downward direction from the upper left to the bottom right. And our data points are again moving in that sort of cloud. These data points are actually a little clustered more tightly than in the previous one, and this is what we're going to call a negative relationship, that as age increases, the appreciation for rock and roll decreases. Conversely, I could have said that as appreciation for rock and roll increases, age decreases. So we're always putting it in terms of as one goes up, the other one goes down. It's not right or wrong to have a specific choice of which one you want to preference when you're talking about these scatter plots. So in this case then, we're talking about that if both the variables are ordinal or interval ratio, we can talk about the direction as well as the pattern. And in positive relationships, we're saying how they vary in terms of their direction. As it increases, so does the other one. But in a negative relationship, they go in the opposing directions. As one goes up, the other one goes down, and vice versa. So let's spin this up and talk about interpretations and assumptions. Now, when we're dealing with R, we're talking about Pearson's R, named after the statistician Carl Pearson. And Pearson's R varies between -1 and +1. That's its range. It's never going to be lower than -1 or more than +1. -1 means that you have a perfect negative correlation. +1 means you have a perfect positive correlation. And 0 means there's no relationship. So the farther from 0 you are, the more perfect or more negative or more correlated you are moving towards perfect positive, perfect negative. Now that value is the R value. That value is the strength of the relationship. And I want you to keep in mind, it's not reflective of the steepness of the line. In the previous slides on the scatter plots, we had some that were sort of like this and some like kind of tilting back and forth. So R is not talking about how steep your line is. That's the slope, and we'll get more to that when we get to regression. Here we're talking about how those data points are converging, tightening towards that line. Okay, so we can also refer to R as an effect size. Because it goes from -1 to +1, we can have a plus minus. So we're going to use our French fry size scale of 0.1, 0.3, 0.5. So plus or minus 0.1 is small, plus or minus 0.3 is medium, plus or minus 0.5 is large. Now, I want to give you a little bit of a graphic here because we're talking about strengths of correlations and positives and negatives. It really helps to just kind of put these things out visually speaking. So what we have here are in the center no correlation, or correlation is 0, and the data points are sort of clouded out. As we move out from 0, if we look to the left on that screen here, we're moving on the positive values. These are going from plus 0.1 up through to plus 1 itself. And as it goes towards 1, it's becoming stronger in its correlation. And if you look at this visually speaking, those dotted points are going from that amorphous cloud, and they're starting to converge, they're tightening up, and eventually it looks like a single line of data points. And the same thing happens as we look on the right side of the screen. As the data points go from 0 to -1, the same effect is happening, but it's going in a downward trend instead of an upward trend, and it is going towards a perfect negative correlation. Let's look at this image here. This is a very interesting image, came out of Wikipedia, and we can see all sorts of different ways that data points and plots can look and how the correlations on them could vary. Across the top, we have that same sort of image that you may have seen on the previous slide, where we're depicting no correlation in the middle, and as the data points move towards positive and negative, they become tighter and tighter towards perfect positive and perfect negative correlation, strengthening in their correlation from 0 towards plus or minus 1. The second row here is showing us that interesting phenomena that it doesn't matter how steep your line is. You could have a perfect positive or perfect negative correlation at any steep or any slope of your line other than 0. When it's at 0, it's that flat horizontal line in the middle, and at that point, it is still perfectly correlated, but it's not perfectly positive or perfectly negative. It's just a flat line, because at that point, it doesn't matter how x can vary, y isn't moving, y stays static as it goes. And at the bottom line, this is an interesting one. All of these here are 0 correlation, 0 R values. And in this case, they all take on these interesting shapes and patterns. Now, when you have these interesting shapes and patterns, I want us to keep in mind that correlated refers to a linear relationship. And it's possible for variables to still be associated, but not correlated. All of the different shape and interesting patterns we saw that take on things like U's and circles and W's and these weird, interesting geometric forms, they are associated. They are related. They have ways in which we can describe them mathematically and statistically, but we cannot describe them as correlated. The correlated is going to want to fit a best line through there and bisect it, but it's going to get confused and it's going to report a low correlation value. These have relationships, we just need different tools to model them that are going to be beyond the scope of what we're working on here. So if you ever see things like this, they're related or associated, just not correlated. So let's talk briefly about the assumptions for Pearson's R. They have to be interval or ratio. We can also use ordinals, but if we're using ordinals, keep in mind you want to use that soft rule or 5 or more categories. Otherwise, we have some non-parametric alternatives we're going to be talking about in future videos. And if you want to do significance testing with R, ideally these variables should be normally distributed. The farther they are from being normal, usually the more sample size and things that we're going to need to take into account like we did with previous videos.